Imagine standing on a spacecraft approaching Jupiter for the first time. The swirling storms larger than Earth come into view. The massive gas giant looms before you, 1,321 times Earth volume. As you scan your instruments, you notice something startling. Jupiter's composition, 90% hydrogen, 10% helium, almost identical to our Sun. Wait, could Jupiter actually be a failed star? Jupiter, our solar system's colossal behemoth, dominates the planetary lineup with a mass 2.5 times greater than all other planets combined. This gas giant's striking similarity to our Sun in chemical makeup has led generations of astronomers to wonder, was Jupiter destined for stellar greatness but somehow fell short? Today we're diving into the science to separate astronomical fact from science fiction. When we look at our solar system's architecture, Jupiter stands apart from the terrestrial planets like Earth and Mars. While the rocky planets are composed primarily of silicates and metals, Jupiter resembles our Sun in its fundamental ingredients. The gas giant's atmosphere is approximately 90% hydrogen and 10% helium by volume, with traces of other compounds like methane, ammonia and water vapor, strikingly similar to the Sun's composition. This compositional similarity is what initially sparked the failed star concept. Jupiter essentially contains the same raw materials as stars, leading some to wonder if it might have been destined for stellar status rather than planetary classification. For a celestial body to qualify as a star, it needs more than just the right ingredients. It requires sufficient mass to trigger and sustain nuclear fusion in its core. This is where Jupiter falls dramatically short of stellar classification. Stars generate their energy through nuclear fusion, a process where extreme pressure and temperature force hydrogen atoms to fuse into helium, releasing enormous amounts of energy. This self-sustaining reaction is what makes stars shine and distinguishes them from planets. Scientists have established clear thresholds for stellar classification. To become a true hydrogen-fusing star like our Sun, an object needs approximately 75 to 80 times Jupiter's mass. Brown dwarfs, sometimes called failed stars, require at least 13 times Jupiter's mass to fuse deuterium. Even the fusion of other elements, like lithium, requires significantly more mass than Jupiter possesses. Despite Jupiter's impressive size relative to Earth, it remains woefully inadequate in the stellar context. As one astronomer put it, Jupiter isn't even a failed star. It's not even close to the minimum requirement for brown dwarf status. The extreme pressure at Jupiter's center generates temperatures estimated at about 35,000 degrees Celsius or 63,000 degrees Fahrenheit. While this might seem incredibly hot, it falls far short of the roughly 15 million degrees Celsius needed for hydrogen fusion. Jupiter's structure is believed to consist of 1. A small rocky core, potentially 14 to 18 times Earth's mass. 2. A layer of metallic hydrogen surrounding the core. 3. Liquid hydrogen above that. 4. An extensive gaseous atmosphere of hydrogen and helium. This structure is fundamentally different from a star where the immense gravitational pressure at the core creates the conditions necessary for fusion. Jupiter simply lacks sufficient mass to generate the gravitational force needed to compress its core to the extreme conditions required for stellar ignition. Perhaps the most compelling evidence against Jupiter being a failed star comes from our understanding of how it formed. According to astrophysicist Alan P. Boss, nearly all scientists who study the formation of planets believe that Jupiter formed in a very different manner than stars form, so that calling Jupiter a failed star is misleading. Stars form directly from the collapse of dense interstellar gas clouds. Jupiter is believed to have formed in a two-stage process. First, a vast collection of ice and rock planetesimals formed and collided to create a planetary embryo. Once this embryo reached about 10 Earth masses, its gravity became strong enough to pull in surrounding gas directly from the solar nebula. This formation pathway is fundamentally different from that of stars or even brown dwarfs, which form through direct gravitational collapse of gas clouds. Despite the popular terminology of failed star, most astronomers agree that this label is somewhat misleading. Dr. Boss emphasizes that brown dwarfs, which are truly almost stars, form like stars through direct collapse rather than the accretion process that created Jupiter. As astronomer Nola Taylor-Redd explains, Jupiter would need to be 75 to 80 times more massive than it is at present to be considered a star. If all of the planets in the solar system had formed as part of the gas giant, it still would not have sufficient mass. Some fascinating facts help put Jupiter's stellar aspirations in perspective. Jupiter's mass is only about 0.1% that of the Sun. Even if you combined all planets in our solar system into Jupiter, it would still need roughly 70 times more mass to ignite fusion. Jupiter actually radiates more heat than it receives from the Sun, but this comes from gravitational contraction, not fusion. While Jupiter may not qualify as a failed star in the scientific sense, it remains an extraordinary celestial body that defies simple categorization. As the dominant planet in our solar system, it has played a crucial role in shaping our cosmic neighborhood's evolution and protecting Earth from potentially catastrophic impacts. Jupiter's massive gravitational influence helped clear the early solar system of debris and continues to shield inner planets from comets and asteroids. Its complex atmosphere, with the iconic Great Red Spot, a storm that has raged for over 350 years and is larger than Earth, showcases atmospheric dynamics on a scale unparalleled in our solar system. So while Jupiter may not shine through nuclear fusion like a star, it shines in its own right as a fascinating world that continues to yield scientific discoveries through missions like Juno, which has revealed unprecedented details about the planet's gravitational fields, magnetic properties, and atmospheric dynamics. Join the conversation. What do you think about Jupiter's classification? Does knowing it would need to be 75 times more massive to become a star change your perspective on this gas giant?